Okay. There we go. So yeah, where we left off, right? So really great derivation there. Um, so yeah, so the main difference is that in most problems, you won't ever like have to deal with something where the mass itself is changing, which is why this like change in momentum term as a whole can usually be reduced down to just a change in velocity. Uh, but there are some certain like scenarios where you will be faced with something where your mass is also changing. Two classic examples I can think of right now are rockets. If we look at rockets, uh, the force is coming from the force back from the air on the from the thrusters, right? But as that force is being applied, you're also losing mass, right? Obviously, when you're burning up the fuel, the mass of the overall thing is decreasing. And so in that kind of scenario, it's not just your velocity that's changing, it's your mass as well, which is why using your change in momentum over just acceleration, right? dp or delta p over delta t is a little more accurate than just using ma. The other example would be common example is like you have a cart that's like leaking sand or draw or like you're picking up sand or like a vacuum cleaner is picking up mass as it's moving, right? In that case, you would be like losing or increasing mass as you're going on. And in those cases, you would have to use this delta P instead of just MA. Um, so let's apply here. Let's say you have a rocket. Um, Initially, it has a mass of 50 or let's say 500 kilograms. Sorry. Okay, Tommy. Yeah, initially it has a mass of 500 kilograms, and it starts at rest. That's a little too easy. Let's say at one point in time, it's moving at 2 meters per second, right when it's off the ground. And then later on, it has a mass of 250 kilograms, and it's moving at, I should probably write this down, or Kevin, if you can write that down in the chat.
Yeah.
Later, yeah. So start out with 500 kilograms, and it's at moving at 2 meters per second. Later on, you have it's at 250 kilograms, and it's moving at uh, 20 meters per second, or say like 10 meters per second. Uh, and let's say that change happened over a time of 5 seconds. What would be our net force on the object during that time? We'll come back in like say five. We'll come back in 2 minutes. Get an answer at that time. Okay. Um, Newtons. Okay, so we want to answer. Do any of you guys want a little more time at that, or 300 newtons? So everyone's getting. Yeah. Soham, you want to walk them through how that works?
All right, yeah, sure. All right, so should I just explain the problem? Like the
Um,
answer?
yeah. Explain like the solution, and then also like write it down. I think you have the ability to annotate. So.
All right, it's like, let me just find my, oh, yeah, I do have, all right, this should work, right? All right, let's see. So you have, let's see, 500, oh my God, this is 500 kg, right? So guys, what's momentum? Someone give me the equation for momentum. Just yell it out.
P is equal to mv.
Yeah, all right. So we have 500 kg and it's moving at 2. So what's 500 times 2?
1000.
Yeah, so you have 1000 as your initial momentum, right? 1000. Yeah, okay. And so now let's look at the second part. The second part is it has a mass of 250 and it's moving at 10. What's 250 times 10?
2500.
All right, 2500. So this thing right here means a change in momentum. So 20, if you do 2500 minus 1000, what do you get?
15.
1,500.
Yeah. You plug 1500 in here, right? For this uh, time change, it literally tells you it's over 5 seconds. So what's 1500 divided by 5?
300.
300.
Yeah, 300. And that would be our answer.
That's exactly how you'd go about doing that. So notice here, if you just tried to use MA and just tried to use your change in V over change in T, you wouldn't know first off what mass to use for the um you wouldn't know what mass to use to plug in, and then two, whichever one you choose, you would be wrong because you have a changing mass, which is why in this kind of scenario you would use delta P over delta T. Um, Let me try something here. Okay. Sorry, guys. Yeah. So yeah, great job. I think you all applied that correctly. Any questions about uh how you would apply this or when to use this, when not to use this? Um, Again, you'll get assignments. You'll have lots of practice problems to do. If we're all good with that, if we're all good with that, then we can go on to impulse as the last thing for today. Oops. Oh yeah, wait. How do you remove Soham your thing?
Oh, that's a good point. Eraser. I don't know if I'm doing this correctly. Oh, can you just
That's
swipe
good.
through?
Yeah, that's good.
Whoa, that's tough.
Oh yeah, it seemed to work pretty well. Um, so here we go. This is a quantity we call impulse. Impulse is denoted by the letter J. Um, again, one of those things that I don't really know. I know I and J used to be the same thing in the alphabet. Used to be like just I, so that might be why we use J. Um, Again, not really sure. But impulse is generally denoted with a J. And so what is the quantity of impulse? Actually, Kevin, you go ahead and take this one. Done a lot of explaining today.
So, I guess
Bobby, Tirina.
a great way to start is to go back to the we can like look at the other equation. We had um F net equals change in momentum over change in time. And so basically what we did here is just we multiplied both sides by change in time. And so we got F net change in time equals change in momentum. And then we defined um F net times change in time as impulse. And I think physicists physicists did this because like force usually in real life, um force is like not really just like applied, like it's not applied like consistently. So like um incorporating that time factor instead of just having like um force at an instant is important. And so they just defined impulse as that. And so we have impulse equals force times change in time, which is also equal to the change in momentum. And so that's basically how it kind of came about with impulse.
Yeah. So that's went ahead a little bit. So impulse is just a quantity we define force times time. It's a good thing you bring that up. Um, a lot of the times, or almost all of the time, you'll never have a constant force. We have oftentimes changing force, and force oftentimes changes with time and with position. Um, and so that'll impact our impulse and our work. And there's no really good way to account for that without taking integrals, which is a calculus thing, so you don't need to worry about that at the moment. But just think about impulse, right? Obviously, if I apply a force on something for 1 second, that's going to produce a different effect than if I apply a force for 3 seconds, right? Um, and so uh, impulse is just a useful quantity to kind of show another sort of magnitude of force being done. How much a quantity of force, I guess. It's just useful to show that obviously that there's a distinction in the amount of time you apply force over. And as Kevin was saying, it's an important quantity because we have this thing called the impulse momentum theorem, which is essentially that J, our impulse, right, our force times our time, is just equal to our change in momentum. You can kind of think of this as very similar to the work energy theorem, where our work was equal to our change in kinetic energy. Here, our impulse is equal to our change in momentum. And all four of these quantities are very closely related. They all arise from basic principles, right? And so they are very closely related mathematically and physically, which is why they often take like the same kind of form of equation. But yes, this is the impulse momentum theorem. J equals delta P or change in P2 minus P1. Um, so this one's a little more difficult to grasp momentum or impulse, sorry. Do you have any questions about impulse? Why do we have it? Units, things like that. Fine. All right. Let's do practice problem. Let's say I apply a force to an object of 7 newtons, and I apply it for uh 93 seconds. What was the impulse delivered to that object? And 51. Yeah. That one's simple. You're just multiplying. Um, impulse. This one's a lot less commonly referenced, but yeah. So yeah, that's a little more basic. If we want a little more uh uh complicated problem with this, let's say I deliver an impulse of 600 Newton seconds. Yeah, let's say I deliver an impulse of 600. And my final two, okay, let's restart. 600 Newton seconds of impulse to a 50 kilogram object. Um, and at the end of the time interval, it is moving at uh 2 meters per second. what yeah, what was my initial velocity? Um Let me write that down. Or Kevin, if you have that here. Oh yeah, you got it. Oh, okay. Yeah. Oh yes, unit, sorry. Um yeah, I'll type the question out. Yeah, so it's just force times time, so newtons times seconds. So yeah, 600 Newton seconds delivered to a 50-kilogram object. At the end of the time interval, it is moving at 2 meters per second. So what was its initial velocity? Kind of go around for this one, so I'll give you like a minute or two. Just put your answers in when you have it. Okay, 10. Just 10 or okay. Close, -10. Kevin, you want to walk through this one? This will be the last thing, guys, and then we'll. Uh,
So, in the question, it gave us 600 Newton seconds, and then it didn't directly state impulse, but we know that the impulse is in Newton seconds, so um we have 600 as the impulse, and then we know the mass is 50 kilograms, and at the end it is moving at 2 meters per second. And so if we remember our formula, um basically impulse equals change in momentum. So um we have um hold up, 600 equals we have our mass 50 times some velocity vi, I'm gonna call it some initial velocity, plus um plus 100, which is basically just 50 times 2, so plus 100. And then yeah, so we can subtract both sides by 100 to get 500 equals 50 vi, and then we can divide both sides by 50 to get just vi equals 10 meters per second.
yeah, almost. Just be mindful of your signs here. Um, because it's subtracting final minus initial, you're actually starting at -10 meters per second.
Oh yeah.
Yeah, so yeah, because you'd have -500 over 50. So just thinking about it, right, if I'm applying a positive force, and the initial momentum is so small, then it probably started with a negative. velocity. Just signs there. But yeah, that's impulse momentum. Any questions? You'll get a lot of practice with these kind of assignment. No here. Let me stop. Okay. Um, nothing. You guys all kind of grasped it, I hope. Oh wait, sorry. There's a question. The P2 momentum is 100. So as a final, the initial velocity -10. Yeah. So we have our impulse, which is 600, minus our final velocity, which is 100, equals the negative of our final momentum, which is 100, equals the negative of our initial momentum. So 500 equals negative G1. And remember our mass, it's mass times velocity, and our mass is, what was it, 50? So 50 VI. So VI equals -10. I think your confusion might have been in momentum versus velocity is not always written as a positive. You could have a negative velocity, and depending on your convention, that could most likely be down or to the left. Because in one dimension, it can indicate a direction. So yes, velocity is can be negative or positive. Um, oh yeah. Then yes, that would it's confusion. Um, yeah. So velocity can be either negative or positive, and that can be used to determine its sign or its direction. Yes, I know we're a little over. So if you don't have any questions, you're all free to go. It'll be in the next couple of days. Again, you'll get a notification. We can probably send out an email about it too once it's up. Um, I'll see you guys Saturday, I guess. Again, email me with any questions you have or the other physics coaches. Yep. You're all free to go then. Sorry, we went a little over.